Okay, we're on the second topic of the pre-physics unit. This topic is significant digits. So the premise here is that it is impossible to make a perfect measurement. Anything that we measure in this class, which is mainly distance and time, is limited in accuracy to the accuracy of the instrument used. Most distances and times can only be measured to 3 or 4 digit accuracy by the methods that we use in our class. This could be a ruler or a meter stick. For time, it's a stopwatch. A little more modern, a lot of us have a very good stopwatch on our cell phones. But it is also limited in accuracy. Most of them go to seconds and then hundredths of seconds. But you can't get more accurate than that on a cell phone, at least not with the standard stopwatch that comes with it. Therefore, we can't report a result in one of our experiments to a greater accuracy than our measurements. So the basic idea so far is that if my instrument could only measure it to 3 or 4 digits, then my results in the experiment couldn't go past 3 or 4 digits. So for an example, let's find the area of a student desk. So I am in my classroom, I have a meter stick, and I'm going to measure the area of a student desk. So I will draw along as I go. All right, so here is basically a desk in my room. They are tables that can fit 2 people. So the depth of the desk, I'm measuring it at 49.5 centimeters. I am looking at my meter stick, and it has 100 increments for centimeters. Each centimeter is divided into 10 smaller pieces, and so I am measuring it at the 5 millimeter marker. So 49.5 centimeters. And for the width of the desk, I've got it at 129.2 centimeters. Now, a problem I just had with that measurement is that my meter stick is 100 centimeters, and I had to move this meter stick. Anytime that you have to start over using a piece for measurement, you're going to introduce some inaccuracy. So these are the dimensions of my desk, and putting it in my calculator, I have 6,325 4 centimeters squared. So if you look at our original measurements, we have 4 digits of accuracy in the width. We have 3 digits of accuracy for the depth. So the idea of significant digits is that we can only have 3 digits of accuracy. So we should report this answer as 6,400 centimeters squared. And you'll notice this only has 2 digits because, as we'll find out later, these 2 zeros don't count the way it's written. So put a bar right there. And that's really an older system of use. It's not very common anymore. But what this bar represents is that this 0 is a significant digit. It does not mean the same thing as in math after a decimal where you put the bar above to mark repeating. They're two different things. And I think that's a big reason why this method is not so much used anymore. What we would do today, the better answer for this would be 6.40 times 10 to the third centimeters squared. And as we'll talk about soon, this 0 at the end of the number, at the right of the decimal, it is significant. Similar idea. So I have an 8.5 by 11 sheet of paper. So we want to know the diagonal of this 8.5 by 11 sheet of paper. So here's what we're looking at. Here is the paper. And we are looking for this. We'll call it C. Since we have two legs of a right triangle, that would be the hypotenuse. So we are looking for C squared equals 8.5 squared plus 11 squared, solving for C. Coming out of the calculator, we get a very long decimal, 13.90143877, and that's inches. This is what my calculator told me. And in fact, my calculator probably rounded this number. If you had a calculator that could show more digits, if it had a greater screen size, this number probably would have gone on. Your calculator rounds to the point where it can show it on the screen. That doesn't mean that this is the answer that we should use. This is way too accurate. I did not report something down to the millionths, 10 millionths of an inch. That's nowhere close to my measurement. My measurements were 2 digits here, 2 digits here. So really we would be reporting 14 inches. So I'm going to write that here, and then I'm going to slightly modify this. Let's say we had 8.50 inches and 11.0 inches. And so each of these has 3 digits. This 0 is important. So is this 0. So with 3 digits, we would report this long number as 13.9 inches. And the way this works is the biggest number is the most important. So this one in the tens place, this one needs to be there. The next smallest one in the ones place, that's the next important, it needs to be there. The tenth place is the next important, it needs to be there. This one, the 0, that's beyond our accuracy for this specific example. We would not include that in our answer. However, we do depend on this one to see how it rounds. Now 0 does not round up, and so the 9 stays a 9. But that next place, so we have 3 digits of accuracy, that 4th place is the one that determines the rounding of the final number. Now, in this class, we're not going to be as strict with significant digits as some other science classes, especially if you remember chemistry. We were very strict on that. Your college physics class will be very strict on it. So I'm not going to be very strict, but however, I expect you to follow the rules fairly closely. Let me state one general rule. You can't have an answer that is more accurate than the values used to get that answer. So we're not going to be very strict with significant figures, but I never want to see something like this. I don't want to see every number that your calculator gives you. I want you to follow the rules closely. Here are some more specific rules. Number one, round off addition and subtraction answers to the least number of decimal places found in the values being added or subtracted. This is for addition and subtraction specifically. Round off multiplication and division answers to the least number of significant digits found in the numbers being used. These two things are different. They operate differently. So you need to take a look at this, figure out what the difference is, and then make sure that we follow the rules for those. Here are some numbers with three significant digits. 235, 4.76, 2.03, 70.2, 32.0, 0.130, 0.000287, 304,000, 2.96 times 10 to the fourth power, 80,000. This one actually does not have three significant digits. If you wanted this one to be three significant digits, 8.00 times 10 to the fourth power. Some numbers with four significant digits: 3,864, 2.489, 20.45, 3,006, 0.09802, 4.050, 0.0002001, 3.201 times 10 to the minus fifth power, 3.000 times 10 to the eighth power, So what's going on here is that if the number is between 1 and 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, it is automatically significant. The only ones that we had that were in question were zeros. So let's look back up at some of these. So 2.03. We have a zero in the middle of two non-zero digits. That automatically makes this one significant. That's why 2.03 has three significant digits. Same thing with 70.2. It's between two non-zero digits. This next one, 32.0, has three significant digits. The reason that this 0 is significant is because it is at the end of a number and there is a decimal point present in the number. The point of this 0 is to show accuracy. They want us to know that this is not 32.1, this is not 31.9, this is 32.0. It shows a certain level of accuracy. In this next number, 0.130, we have two non-zero digits. Those are automatically significant. So we have to figure out which of these zeros is the important one. Is this 0 important, or is the final 0 important? Which one shows the accuracy? Which one tells me that this is not 0.129, not 0.131? This one, the 0 at the end of the number when a decimal is present in the number. In a similar idea, look at this one over here, 0.000287. This number has three significant figures. It has three non-zero digits. So this one, and this one are significant. And that tells me that all of these zeros to the left of the number are not significant. Those numbers serve a function of telling me how small this number is. It doesn't tell me anything about accuracy, it just tells me the relative size of the number. Easy way to figure out, are these important? Do they disappear when you put it in scientific notation? All of these zeros disappear over here. On a similar train of thought, this times 10 to the minus fourth. This scientific notation, times 10 with its exponent, does not count towards significant digits. Just as in this example, 2.96 times 10 to the fourth power. It has three significant digits, 2, 9, and 6. Times 10 to the fourth just tells me the relative size of this number. Looking at our numbers with four significant digits, some of them are fairly simple. We have all non-zeros. We have a 0 between non-zeros. Same thing here. We have a few that are a little more difficult. So we have this number, 0.09802. The 9, the 8, and the 2 are automatically significant because they are non-zeros. And this 0 in between is automatically significant. The 0.0 does not tell me accuracy. 0.0 tells me the relative size of the number, and therefore it is not significant. Those first two zeros are not significant. In this number, we have a non-zero, one in the middle, 4.050. This last 0 is significant because it shows me accuracy. This is the 0 that tells me it's not 4.048, it's 4.050. So in this next one, we have non-zeros, we have zeros between, and all of these are not significant. They tell me the size of the number. Zero in between non-zero digits times 10 to the negative fifth does not count as significant digits. 3.000, 4 significant figures, times 10 to the 8th power does not count. Okay, so some examples here at the bottom. Formula, this is a made-up formula, but similar to a lot of the formulas that you will find in physics. A lot of them are this simple. R equals C divided by K. If C equals 24.6 and K equals 7.02, find R. So in this class, here's the way that we do this. We start with the formula. R equals C over K. This is a requirement on written homework assignments. You start with the formula, just symbols. Then we're going to go in, we will fill in the number for C, 24.6, and fill in the number for K, 7.02. Only at this point will we put it in our calculator. We are following these specific steps. So we get an answer that is quite long. Calculator says 3.50427735, and it goes on to 3 significant figures, 3.5, and my number is 3.504. So this next digit remains as a 0. That's 3 significant figures. We had 3 significant figures for C, 3 significant digits for K, and now we have 3 significant digits for R. Just as a note, I slipped up and said significant figures just a second ago. Significant figures and significant digits mean the exact same thing. In chemistry, we typically call it significant figures. In physics, a lot of times it's called significant digits. But just if you hear me say significant figures again, know that it means the same thing as significant digits. Number 2, here's our formula. A equals M times D. So first thing I'm going to do in my work is write the formula. That's going to be a requirement for all written assignments. M equals 3.6 and D equals 2.7. So I'm going to fill in my numbers. 3.6 times 2.7. Just as a note, each of these has 2 significant digits. Now that I've written my formula and what I'm going to put in my calculator, now I'll put it in my calculator. Calculator says 9.72. So 9.7, the next digit is a 2, which will allow this 7 to remain a 7. It will round it down. 9.72 becomes 9.7. Another formula, H equals T divided by W. If T equals 34.16 and W equals 2.03, find the value for H. So we've written everything down. We're going to put it in our calculator. Calculator says 16.8275862, and it's running out of room. Now we have to figure out how many significant digits do we need. So let's take a second. This number right here, 34.16, that has 4 significant digits. 1, 2, 3, 4. And W has 1, 2, 3 significant digits. So we have to figure out, do we want 4 significant digits in the answer, or do we want 3? Well, this is where we come back to our specific rules. Multiplication and division answers to the least number of significant digits found in the numbers being used. That would be this one. It has 3 significant digits. That is the least number of significant digits. This one determines the accuracy of our answer. So my answer should be 16 point, the next digit is 8, and the digit after that is a 2, which will leave the 8 as it is. Our answer is 16.8. Formula P equals A plus B plus C. If A equals 2.347, B equals 9.34, and C equals 1.0536. Find P. So P equals A plus B plus C. The reason we do this, the reason that we write the formula with the symbols, is so later on you know what you did. I've had too many interactions with students where I ask them, how did you come up with this answer? And they reply, I don't know. If your reply is, I don't know how I got that answer, it means that you didn't learn it, you don't know it well enough. This is why we write it every time. Repetition leads to improvement, and seeing what you did on paper will be a reminder later. So when I call you up to my desk, you will at least know what you did on paper. So we fill in our numbers. 2.347 is my value for A, plus 9.34 is my value for B, and 1.0536 is my value for C. So I'm going to put them all in my calculator. Calculator says 12.7406. So maybe I'll write that off to the side. 7406. This is the calculator answer. But there are rules. So look back at the top of the page. We added here. Rule number 1, round off addition answers to the least number of decimal places found in the values being added or subtracted. So let's look at decimal places. So here, A, we have a number with 3 digits after the decimal. B, we have a number with 2 digits after the decimal. And C, we have 4 digits after the decimal. So B, 9.34, has the least number of decimal places found in these values, which means we're going to round it to 2 decimal places. We're going to round it to the 100th decimal place. So looking at my calculator answer, 12.7406, I am going to round it to 2 decimal places. So basically what you see is 12.74. And here's the final note. The reason that addition and subtraction only deal with the numbers after the decimal. When you get to adding numbers, it gets bigger very quickly. So if you added two numbers, you might gain, well, let's just do an example. 5 plus 6. Here we have one significant figure. Here we have one significant figure. The answer to 5 plus 6 is 11. But this has two significant figures. We want 11 to still be 11. We don't want 5 plus 6 to be 10. 5 plus 6 is not 10. So we want this to be accurate. 5 plus 6 is always 11. It's just fact. If you put it in your calculator, it's a fact. We're not going to round this. But if we had 5.1 plus 6, so now we have 1 after the decimal, and then really this is nothing after the decimal. That's what you're looking at. This would be 11.1. 5.1 is a little more accurate than just 6. And that's why this 0.1 drops off.